Okay, to look at how we're going to apply those formula, let's look at let's do one example on the combined curve. So what we're given here, you're asked to calculate the setting out data for the combined curve, and the variable is given intersection angle, which is 23 degrees 30 minutes, radius of circular curve of 450, the speed of velocity 60 kilometers per hour with a rate of change of radial acceleration 0.3. Change of I given as 1550 to 35, and you're told your circular curve should be set at 20 meter interval and your transition curve at 10 meter interval. So what are the preambles? So what do we need to calculate? We're going to need to calculate the initial values or starting values. Okay, what are the things? So we need to know the length of the transition, which is in this case 34.29. S, the shift. Remember that we have to bring down, we have to move the circular curve from its supposedly original position so that we could fit in the transition curve at both ends. Then the tangent length, between the tangent length here, meaning the tangent length of the combined curve. The changes, T1, first tangent point, T2, the second tangent point, should also serve as a common tangent point between the transition and the circular. Then phi max, the maximum deflection angle, delta max, that's for transition, which is 43 minutes 40 seconds. Then the length of the circular curve, LB, which is 150.27. Then we move on to changes T3, the next common tangent between the circular and the second transition curve, and the final tangent point before we hit the second straight. And the last value here, deflection angle, but this time deflection angle for circular, which is given by 9 degrees 34 minutes. Okay, so we are using all those figures, okay, to come up with a table that is normally required before we go out to the field and set out the curve. So in any setting out work, we normally have to prepare some kind of data. So in this case, a table, and before we actually go to the field, we have to double check just to make sure there's no errors in the calculation, because we don't want to end up with putting in points which are wrong, okay, which are not as per design. Okay, let's prepare the first one, the first table for the first transition curve. I'm going to call it transition curve number 1. Okay, so that's from T1 to T2. So that's T1 and that's T2. And we were told that our interval for the transition is 10 meter. So we have 10 meter in there. And as I explained earlier in the previous slides, that the first between the tangent point, the first tangent point and the point on the curve, and the last one between the last point on the curve and the second tangent point, most likely will not be as what the interval wants. So in this case, 0.53 for the first one and 3.76 for the last one. So L basically is the distance on the curve, okay, so that's 0.53. Then this one just simply adding those two numbers to get that, okay. So you add those two numbers to get that. So in the end, you will get the length of the transition curve, which we have calculated beforehand. And based on those L's, okay, we can calculate the delta, okay, which is L squared over 6RLP. Okay, then we got 1 second here. Okay, 4 minutes there, 15 there, 34 there. And for the last point, it's 43.40. you got to double check against the maximum deflection angle, which we have done before, and it agrees. That's what we got, so that one checks out. So we are good as far as calculation is concerned. Okay, something interesting in here, and this is probably worth pointing out, is the first point, that 1440. Okay, it's so close to T1, and it's only about 1 second. Okay, so when you're doing it, actually you are forgiven actually for omitting that point because it's too close. I think it's wise just to ignore that point, just move on to the next one, which is 1450. Okay, so that will be the first table for transition curve number 1, and we've done the check, so we're good to go to prepare for the second one, which is the circular curve from T2 to T3. Okay, and we're going to start with T2. We will finish the table at T3, and we will do 20 meters. That's what we're doing here. Again, for the first and the last, not necessarily 20 meters. Okay, because they are tangent points, and using the formula, which is the chord distance by 2r multiplied by 180 over pi, you'll get 0.39 for that one. Okay, in degree. Okay, I probably made a mistake here. Okay, just ignore that. They're all in degrees. Okay, in degrees, and the rest will be the same because they're all 20 meters chord distance. So you notice that all the numbers here are the same, and the last one is obviously 0.256 811 8129. And I explained earlier that to make our work easier in the field, we sum all the angle because we can set one common zero. Just simply adding up all the numbers in that column there, you come up with all these numbers, and look at your final deflection angle, which is your delta max for your circular, and compare that to what we have calculated before, and you will notice that it agrees, which means that we have checked that the deflection angle is, or the deflection angles are okay. So there's no arithmetic error in there, there's no calculation error, so we've checked. So we're done from T2 to T3. Okay, now I've got to prepare the table for the second transition curve. Okay, and let's call it transition curve T3 to T4. Okay, the thing with this is when we do the second transition curve, okay, T4 is actually the tangent between the straight and the transition curve, whereas T3 is a tangent between the circular and the transition curve. So it is easier to do the work from T4. So when we do this one, when we do the second transition curve, we're going to set it up from T4. Okay, we're not going to set up from T3. So that's why if you look at this table here, we're going to start with T3, excuse me, T3 and T4. That's T3, that's T4. But we're going to start with 0 at T4. Yeah, 0 there at T4, because that's what we are. So we're going to move up first chord, okay, which is 1650. Okay, we're going to start with 1624. We're going to move down 30, 40, 50, and lastly 8.165, 8.32. So this is the interval except for the first and the last. But when we do the calculation, we're going to start from the bottom, 0 there, 8.32 there, then this one is just the sum, and when we get to the last point, which is T3 in this case, that equals to LP that we have calculated. And we're going to calculate all this deflection angle, and obviously Our max deflection angle now will be at T3, which is 0.4340, so that agrees with the value that we have calculated earlier. So remember, the second transition, again I made a mistake, that should be number 2. Okay, the second transition would be set up from T4. Okay, alright, so that's on transition curve, combined curve, to be exact. How do we deal with the numbers and how we put them in nice order in a table, and use those numbers, do all the checks, and before we go to the fill in and set up the, or set out, should I say, set out the center line, okay, the markers at the intervals has been intervals that we require, or intervals that we were told to do. Okay, so what I want you to do next, there's another set of data. Okay, consider this an exercise. Okay, prepare all the 3 tables for that data, and I will post the answer in e-learning. Okay, so make sure that you do this, okay, because if you don't, then you would not have enough preparation for doing a calculation on setting out a combined curve. Okay, so answers will be posted in the e-learning. Okay, so we've done on horizontal curve. Now we're going to move on to vertical curve. Okay, so by early in the chapter, we mentioned that, you know, a curve, in the horizontal curve, is to change direction from one to another. When it comes to vertical curve, it's basically to change one direction. Let's say you're here, okay, you're moving from there to there, so you need a curve at the top so that your right will be comfortable. So in probably another thing that worth noting is that, let me just erase that. Noting is that when we do curve design, okay, the blue line represents the existing shape of the terrain. Okay, probably there's just a hill, okay, and a valley there. So when we design a curve, we're gonna make a grade or a slope. We're gonna average that, maybe whatever that we have decided, and another slope there that we average, you know, of the existing ground. Okay, so we're going to average the slope like that. Okay, we call it grades or gradient. So based on those lines or the grades, which is similar to intersection point in the straight line in your horizontal alignment, so we'll be fitting in a curve which is there. So that is what we term as a circular curve. Okay, curve A and curve B. Okay, that's basically what we're looking at, right? Curve in the vertical plane. So we need those curves, obviously, as I say, an intersection of slopes, or sometimes referred to as grades, or sometimes called gradients. They're all the same thing, it's just a matter giving them different names. Sometimes I will refer them as grade, or sometimes I will refer them as gradient. They're practically the same thing. So, but to why? To provide a gradual change from traveling from one grade line to another. So that's the idea. So that the change that we feel when we're going uphill, then downhill, or the other way, just to make us to provide a smooth, safe, and a comfortable ride. So when we talk about vertical curve, I think you will realize by now that when we going up a hill in a vehicle, our visibility or our sighting distance, meaning that what we could see on the other side of the curve is limited. Okay, so that's why you notice there'll be double lines on the center of the road, just to say that you're not supposed to be overtaking, because you cannot simply see what's coming towards you. So when we design vertical curve, we will think about sighting distance, we will think about safety. Yeah, so those are probably the controlling factors in designing vertical road curve. Then also we will also be talking about comfort to the passenger. If the curve goes, say, up there, going uphill and then downhill, and obviously if we have a nice gentle curve, the ride will be smooth, as compared to perhaps a very short curve like that. So if you have a short curve like that, if you're traveling high speed, you'll practically feel like you're flying, you'll be airborne. Okay, so these are the things that we have to take into account when we talk about vertical curve design. So talking about the curve themselves, there are two types. Okay, whether they are crest curve or sag curve. Okay, I have got so crest curve basically means grade or gradients meeting at summits, whereas sag curve simply refer to grades that meets at valleys. So I think I'll have a link there. So that's a good picture of a crest curve. You could see that railway line, that track is next to the road. There. So you could see that there is a crest curve. Here the train is going down. And in this case here, there's a crest curve over there. But down here will be a sag curve. Okay, so here will be a sag curve. So that's a sag vertical curve and a crest vertical curve. That means at summit and as well as valleys. Okay, so that's a good picture that I got from the internet. I think along the way, from there to there, all the way, you could see there are several crests and several sags, several crest curves and several sag curves. Okay, good example this one. Okay, that one to there. You can see how it goes up and down. All right, then apart from those two, okay, some texts, okay, some references do mention about what they call type 2 vertical curve, which simply says either the curve goes uphill or the vertical curve goes downhill. So what do I mean by that? It simply looks like this. Okay, you could have one going up and the next one is also going up, but with a different gradient, coming down and one coming down. Okay, the same thing here, going up and another up, but in a different direction. That's going down and that's also another going down. So this is what they call as type 2. Okay, it's still a crest curve, but they call it type 2, and that one type 2 sag. Okay, this one they call it as type 1, the one we just discussed. Okay, so it depends. Okay, you could either look at this, you can either look at it this way, type 1, type 2, or just you could generalize them and say we just only have two types, crests and sags, which is either way work just fine. Okay, that's a bit on the type, and when we do our calculations, grades or gradients are represented in terms of ratio, either 1 in 40 in this case, in this example, or just in percentages. Okay? And these two are frequently used, yes? Either ratios or percentages. So rising grades are written as positive, and descending grades are written as negative. So we could have, like, say, plus 5% rising grade, or minus 5% for descending grades. Okay. Now, in vertical curve design, calculations are based on what we call as algebraic difference. I'm going to give a term A. Okay. Some text uses A. So between grade, okay, the algebraic difference. Okay. So how does this work? What does it mean? I think the next picture will explain, will show you. Okay, if we have, let's look at this one first. Let's look at this one first. Okay. So if we have a crest curve that goes m% positive, then minus n% going downhill. So the algebraic difference is basically m minus, this is a minus, so it becomes positive. So in effect it's m plus n. Okay. How about this one here? It's a sag curve. First one negative m, next one a positive m. So it's going to be minus m minus plus m. So it's going to be a negative. The value of algebraic difference will be negative. Okay, and I think you can understand, or you can figure out, okay, all those equations there. Okay, so algebraic difference, we are taking the difference, okay, between the two grades that meet either at a summit or a curve, whether it's a type 1 or whether it's a type 2. Okay, so always m minus n, should we say, put it that way. Okay, right. We will do some examples later so you can see clearly how this is done. Right, that's a figure just to show when we're going uphill. You probably have come across these signs by the roadside, just to show, in this case, 25% going uphill, or in this case 15% going down, okay, or 10% like that. So I think this is what we normally see in mountainous area when we driving. If it's a steep hill, it's a steep grade, they will tell you, okay, so that you'll be a bit more cautious going up or going down at that particular stretch of vertical curve. All right. So when we talk about transition curve, there are 4 types that we use, either a lemniscate, clotoid, cubic spiral, or cubic parabola. So how about vertical curve? So what kind of curve, what type of curve do we use? We'll be able to use a cubic parabola, we'll be able to use a spiral, or we'll be able to use a lemniscate. Okay, let's see how it is. Okay, in vertical curve, what we normally do, what we normally use is a parabola. Okay, so why parabola? Because we do have other kinds of spiral, but they've chosen parabola. Why? Because from the geometric point of view, a parabola gives what we call a uniform rate of change of the gradients. Okay, what does that mean? Equation y equal to, just get a simple parabolic equation. Okay, I'm not going to concern with the constant and so on. Okay, just look at the first term. Y equal to ax squared. Differentiate that, we get 2ax. A double differentiation will get us a constant. So that is a gradient. Okay, double differentiation, which simply means the change of gradient, which is constant. So that's what we're looking at. So that's why we're not bothered with higher order polynomial. So we just fix a simple parabola. So having done that, having adopted that, so we can be sure that we get a curve that provide a uniform rate of vertical radial force, because the change of grade is constant. Okay, this is for comfort purposes. Okay, excuse me. Okay, for comfort purposes. Okay, so the reason. So if you ask why use parabola, so these are the reason. Okay, right. Okay, in order to be able to further use that parabola as related to in relation to vertical curve design, so there are a few assumptions and a few approximation that we make. Okay, the reason that we can make this assumption is simply because the gradients are small. Okay, we're talking about 3%, 4%. Okay, which is small. So that's the reason why we can come up with this characteristic in relation to a parabola. Okay, in true mathematical form, it won't be correct, but we've adopted it for vertical curve design simply because the gradients are small. So what does it say? First, it says the length of the parabolic curve, which is L, okay, which is by right should be that length there. Okay, but we say that it's horizontal, is L, is the horizontal distance. So the length of that red arc I've just drawn is equal to the horizontal line, horizontal distance between A and C. So that's the first, okay, characteristic. Okay. Then second, it says the vertical that runs through B bisects the curve at B. Bisects the curve, I mean, and the distance BD is equal to DE. So this point here actually bisects the curve. So that will be, the curve will be the length will be equal from there on. Okay, from A to D, and from A, from A to D, and equals to from D to C, which is also equal to the horizontal distance, that one there, A to F and F to C. Okay, so that's assumption, the approximation that we make. And the difference in height, the third one there, is the difference in height, DH, which is that distance there, of any point. So let's say that that is the point that we are interested in. Okay? Any point on the grid. So what I have done here, the grid is actually A to B. So I projected it for calculation purposes to B prime. So the dotted line just means it's a projected line. Okay? Grade VB is px prime over 100. So it's basically the distance of that point from A, which is x prime, okay, multiplied by the grade divided by 100, okay, in percentages. Okay, that's basically what it is. And the offset y, that distance there, let's say we have a point there, so that distance we call offset is directly proportional to the square of that distance. So which means that y directly proportional to x squared. Okay, so that's the characteristic. And the distance along the grade AB, that distance there along the grade AB, okay, if I just show A, from A to B, that distance there, okay, is equal to AD, which is equal to AD, half the curve length, and also equal to LAF. Okay, so that's the should I say characteristic or approximation that we make, okay, when we apply the parabola in vertical curve design. So having got all those approximation, we're going to use that characteristic to come up with the subsequent calculation for the reduced level of the point. Okay, so what are the equations? Again, refer to the recommended text if you need a derivation of this. But I think it's here suffice for me just to highlight what the equations are. Okay, the first one is the offset. As I say, it's proportional to the distance. So y, that one there, y is directly proportional to x squared. So the constant being p minus q over 400L. Okay, so this is the algebraic difference. In this case is p minus q, and some texts use a notation a for that. Okay, I'm just going to stick to that. P minus q over 400L multiplied by x squared, and the distance of the highest and lowest point on the curve, okay, which is probably that point there, is 2p over p minus q multiplied by L. I think it's probably worth noting that if I have two grids, both of the same value, different sign, let's say minus p plus p. So if I fit in a vertical curve in there, obviously my highest point will be just below the summit. Okay, in other words, if you compare that to this diagram here, okay, let me make my cursor correct. If you compare that point with the diagram here, so D is the highest point. Okay, D will be the highest point, but in most cases the grades are not equal. Okay, we might have P this way and another one that way. So we might have plus. I made a mistake there. Somebody, sorry, excuse me. I can just probably delete. That should be plus. That should be minus. Okay, because I'm going from there to there. All right. So if I have plus P there and minus Q now, which is lesser than P. So when I fit in a circle, when I fit in a vertical curve, okay, it might look something like that, where the highest point now is nowhere under beneath the intersection point, but it's somewhere else. So that's what I'm trying to show in this diagram here. Okay, P might be there. Okay, because that grade and that grade are not equal. So how do we tell where that P is? We can calculate that distance. Okay, that distance from A to the point on the grade where P is, the highest point is, I mean. Okay, so which is given by the equation. So the distance of the highest point from A will be on the grid will be 2p minus 2p divided by p minus q over L, and the reduced level of M, which is a point. This is a level on the curve at M, which is here. Okay, okay, will be the reduced levels of A. Okay, and plus dH minus y. So I will have a dH there. So reduced level of A plus dH minus y. So that will give me the reduced level of M. Okay, of point that we require to mark on the curve. Okay, so that's how we come about with the reduced level. Okay, reduced level. That's what we want. Reduced level of the curve. Okay, at M. Right now, when we look at horizontal curve, the length of the horizontal curve, the transition curve. we know that it's a function between the velocity, the radius. Okay. So how about vertical curve? What are the factors that we take into account when we talk about deciding on what the length would be? Okay. Okay. Right. There are two basic items that we look at, or three in a way. Sighting distance. Okay. We're going to ensure that the curve that we provide is safe enough and is safe enough for drivers. So for that sense, we have what we call is a stopping sight distance and overtaking sight distance, and some refer this as a passing sight distance. Okay, passing sight distance. Okay, they're simply the same thing. Okay, so stopping sight distance simply means that when you're going uphill, imagine you're going uphill, as soon as you see something, obstruction or object in front of you, how long a distance that you need to stop. Okay, so that's stopping sight distance. Overtaking, I think, is self-explanatory. When you want to overtake a vehicle in front of you, so how far ahead can you see? Okay, so that will be safe for you to overtake. Then we have comfort. Okay, in terms of comfort, we will try and look in the with respect to vertical radial force. We try to reduce them, and it only applies to sag curve. Okay, when we talk about comfort, only applies to sag curve, and obviously there are standards that we can use. Okay, we can refer to that make our life easier as far as design is concerned. To decide on the sight distance, there is standard, and also what we call the key values. We'll come into that later in next few slides. And the governing body, as I mentioned earlier, is JKR. So we're going to base on the standard given by JKR.
انضم معنا الآن واشترك بالقناة ليصلك كل جديد. YSAG، معا نحو مستقبل مشرق.